Okay, good morning, Thermal 1 class. I thought I would record the solution to the test. I'm not going to be able to be in class on Tuesday, so I'm going to record this and then I'll record some lecture. And I will post them both and email this all out to you so you can watch it at your leisure. Okay, so as far as the test is concerned, let's go ahead. I've got this in preview mode. And so let's go ahead and take a look at the solution of it. So question one, geothermal power plants use underground sources of hot water or steam, excuse me, to produce electricity. If the plant receives hot water at 350, so that would be the high temperature reservoir that's going to transfer into this power cycle, and rejects energy by heat transfer to the atmosphere at 60, the low temperature reservoir sink. What is the maximum possible efficiency for the power plant? So we want the Carnot efficiency. So this problem is really pretty simple. But at any rate, so here's the picture. We kind of draw this high temperature reservoir, 350 Fahrenheit, low temperature at 60. And so we're transferring heat into our power cycle, rejecting heat required by the second law, and we get some work out. So the equation for the maximum possible efficiency given these temperatures is just 1 minus Tc over Th, and we have to use absolute temperature, so we just have to convert the Rankine. So we add 460 to both of them, so the 350 becomes 810, and the 60 becomes 520. So plugging in the expression, we get 0.358 or 35.8%. So that rounds to 36, and so there's number two. Air modeled as an ideal gas enters a turbine operating at steady state at 1040 Kelvin and 278 kPa and exits at 120 kPa. Mass flow rate is 5.5 kilograms a second. Power developed is 1120 kW. Spray heat transfer, kinetic potential energy effect are negligible, so we'll draw that away. Assuming K, the specific heat ratio, is 1.4, determine the isentropic turbine efficiency. Okay, this is a little bit better problem. First one, this is one that, yeah, I just took this one out of the back of the book. So I had it, so there's a solution, manual solution to this one. So it's a lot neater than what I would write. So on the TS diagram, see we have an isobar at the high pressure, which kind of swoops in like this. And then we have an isobar at the lower pressure, one's a constant pressure on TS diagram, like that. So this is our inlet state, high pressure, and we're showing that at 1040K. So we've got two different turbines here, right? Because the isentropic efficiency is a comparison between a real turbine and an ideal turbine. The ideal turbine operates with no entropy increase. So from one, we drop straight down on the entropy scale until we get the lower pressure. And that state we call 2S to remind us it's entropy. The real turbine produces some entropy as the fluid, as the air flows through it. And so we bend over here and wind up at some state 2, which is at a higher temperature than the isentropic state. So we'll have a different enthalpy. Okay, well, let's take a look at this. There's the picture with all the information given. And so, okay, so if we write the first law for this, then it'll boil down to DECV dt is 0 because we're steady state. The heat transfer term is thrown away because it's basically operating adiabatically. And so without the Q dot CV term, we get minus W dot CV, which would be the work produced by the turbine, plus the mass flow rate times H1 minus H2. This is the enthalpy of the fluid in, specific enthalpy in minus specific enthalpy out times the mass flow rate, because the kinetic and potential energy terms are gone. Okay, and then for an ideal gas with constant specific heats, which is inferred by constant K, which is the specific heat ratio, then we know that this enthalpy difference, H1 minus H2, is Cp times T1 minus T2. Pretty simple. And so then we're going to substitute Cp times T1 minus T2 into this expression for H1 minus H2. And then we're going to solve for T2. So we put this in for here. We have then we have mass flow rate times Cp T1 minus T2 inserted as part of this equation, and then we simply divide through by m dot Cp, and that clears out temperature. So then I can move T2 to the other side of the equation, and bingo, I have an equation that will calculate T2, which I need to determine the enthalpy at this state. This is isentropic. So I have equations that I can use directly this enthalpy to determine this temperature. Okay, so I need a specific heat, and so I'm told that I'm given K is 1.4, and so this little expression allows me to calculate Cp from K using the specific gas constant. So Cp is what K, 1.4, times specific gas constant, which is universal gas constant, 8.314 divided by 28.97, which is air, divided by K minus 1. And so when I do that calculation, I get 1.004 kilojoules per kilogram per degree. K is my value of Cp, and then I'm going to substitute in this expression and calculate T2. So T2 is T1 minus the work, and this is work produced by the control volume into the surroundings, so that's positive work. So it's minus a positive 1120, then that's divided by the mass flow rate, 5.5 kilograms per second, and times the specific heat, 1.004. Some unit conversion going on. 1 kilojoule per second is kW, and so to get my units to cancel properly, it doesn't change the number, but it makes the units work. So I see that T2 up here at my state 2 is 837.2 Kelvin. Now, my definition of isentropic efficiency is the turbine is the actual turbine enthalpy difference, H1 minus H2, divided by H1 minus H2S, and this is the ideal turbine in the denominator. So I can substitute in Cp delta T for both of these, and then the Cp's will cancel. So my expression for the isentropic efficiency of this turbine is T1, the entering temperature, minus the actual T2 exit temperature, divided by T1, the entering temperature, minus the isentropic exit temperature. And then to get T2, we recall for an isentropic process, an ideal gas with constant specific heats, we do T2S over T1 is quantity T2 over T1 raised to the K minus 1 over K power. So this gives T2S, and then I have all my temperatures, and I just plug in this expression, and I get 1040 minus 837.2 divided by 1040 minus 818.1, and so that's 91.4%. So that's the answer to number 2, 91.4. Okay, so we'll go on to the next page. Question 3. I've got steam at 4 megapascals and 400 degrees C is throttled adiabatically through a partially open valve to a pressure of 1 MPa. If changes in kinetic potential energy are negligible, the specific volume of the steam after throttling will be. Okay, So this is just a throttling process, I guess. Let's see, that would be this chapter 4. So if we just look back, let's see, here, throttling devices. And so just this is the definition of a throttling device. And then when I apply the first law to it, everything drops out except the m dot times the enthalpies. I can divide the m dot out, and so I get each one. That's what the first law says. Okay, so I know that the enthalpy is constant across this device. So I'm at 4 MPa and 400, and I'm going to 1 MPa. So let's call up the tables here, and let's do 4 MPa, and here's 400. And so there's my enthalpy, 3213.6. So the enthalpy is not going to change as I go to the lower pressure. And then I have to take this enthalpy to the 1 MPa tables, 3213.6 and 1 MPa. So 3213, I'm in between 360 and 400 in terms of temperature. So I have to take this enthalpy, my 3213 enthalpy, and this enthalpy, and I have to interpolate here, and then apply that interpolation to specific volume over here. So that's basically okay. Yeah, that's the first one that I worked. Okay, and so there's my 3213.6 at it's 40 bar, which is 4 MPa, 400 degrees C. So I just made copies of numbers out of the table, 360, 3178. Leave a line for my result. So I know my enthalpy at MPa is going to be 3213, and then at 432. So I do the interpolation of the specific volume up here at 360. 2873 at 400 is 0.3066. So then I interpolate and determine my specific volume is 0.2952. Back 2952. Question 4. Helium gas is to be heated steadily with a 3 kW, and a kW is a kilojoule per second, mind you. Electric resistance heater as the helium flows through an insulated duct. The helium enters at 50 C at a rate of 0.08 kilograms a second. The exit temperature of the helium will be the following. Note for helium, the specific heat at constant pressure. The C sub P with a hat on it, because it's a molar value, is 5/2 or 2.5 times the universal gas constant. So we'll have to use that. Okay. Here. There we go, helium gas. Okay, so I just restated the problem. Okay, so I've got to determine my CP value. And so universal gas constant, 8.314 kilojoules per mole per degree K. And then this is molecular weight of helium, 4.003 kilograms per mole. And so my CP is the universal gas constant divided by molecular weight. And the first time I left the 5 halves out. I had to go so I stuck in the 5 halves. 5 halves times the 2.077 is just this division. Got to be multiplied by 2.5, which the result of CP is 5.1924 kilograms per degree K. Okay. First law says dE/CV/dt is 0 for steady state. Then the rest of the terms would be the heat transfer term minus the work term plus the mass flow rate times H in minus H out. And I'm going to substitute in Cp delta T, or Cp Tn minus T out for the enthalpy in minus the enthalpy out. So I make that substitution here. And let's see, I bring this term to the other side of the equation, which switches the temperature from Tn minus T out. First it's enthalpy, and then I make the substitution. So I bring this term to the other side. I throw away the Q dot term because we're insulated, and then I make the substitution. H out minus H in is Cp T out minus Tn over here is equal to negative of the work, and so I solve for T out. And the expression is negative of the work divided by m dot Cp plus Tn. And this is this work is negative because it's the surroundings doing work on the fluid, so the heat, electricity is flowing into the control volume. So it's negative times negative 3 kilojoules a second specific heat, and the mass flow rate. These are multiplied together, and just plug it in here. Add on the 50 degrees C, we get 57.2. Now this says degree K up here. As long as it's a temperature difference, you can work it in degrees C or degrees K, because if I convert this, I add 273 to this number, and I add 273 to this number, but this is the negative of it, so the 273 on this number cancels out 273. So the delta T is the same, whether you do degree K or degree C. So that allows you to go ahead and work directly in degree C. In this case, if you don't want to do that, you can convert everything to degree K and then back to degree C, and you'll get the same. So we get 57.2. Page. Okay, 5, we have an adiabatic heat exchanger is used to heat cold water at 8 degrees C, entering at a rate of 3 kilograms a second, by hot air at 150 degrees C, entering at a rate of 3 kilograms per second. So we get the same mass flow rate of the water and the hot air. If the exit temperature of the hot air is 30 degrees C, so it's cooled down 120 degrees C, the exit temperature of the cold water is which of the following? Use constant specific heats evaluated at 300 K, because when you look them up, you have variation in temperatures. OG1 to use. Okay, so on that one. Adiabatic heat exchanger. Here we go. Okay, well, let's go look at PowerPoint. Heat exchanger. So this was out of the lecture note. So basically, you got water in, water out, air in, air out. And so when I apply the first law, this is the full-blown version for a steady state, and I throw out the heat transfer adiabatic. There's no work involved. Throw out kinetic and potential energy, and so this boils down to summation m dot n times Hn minus summation of m dot out exit out is going to equal 0, and so I can take the equation. And so that's where I'm starting here. Summation of on the inlet side of mass flow rate times enthalpies is equal to the summation of the exits of the mass flow rate times enthalpies. So then just breaking this apart, I've got mass flow rate of water because the water in is equal to the water out, and the air in is the air out in terms of mass flows. I've got m dot W times H water in plus m dot air times H air in is equal to m dot water times H enthalpy out plus m dot air out. So that's my expression. Looking up my CPs from the table, you should get water 4.179 kilojoules per kilogram per degree K, and air is at a bobble 1.005 kilojoules per kilogram per degree K, and then just plug in the numbers in. And I brought the water term on one side and the air term to the other side, and then plugging in for the water, I get 3 kilograms per second. Specific heat of water times T2 minus 8, the entering temperature. And on the air side, it's the same mass flow. There's the specific heat of air, and I know both temperatures, so that's 150 minus 30 is 20. And then I solve this, so I can throw the 3's away, and I do the arithmetic to solve for T2, and I get 36.86. So 36.86. Okay. So question number 6. System executes a power cycle while receiving 1050 kilojoules of heat transfer at a temperature of 525 K and discharging 700 kilojoules to the low temperature tank at 350 K. There are no other heat transfers to determine whether the cycle is internally reversible, irreversible, or possible. So let's take a look at this. Look. So this just restates everything. So there you go. A couple of different ways to do this. You can do it, you can check the entropy production, which is what we're doing here. And so the negative of the cyclic integral of delta Q over T. And so we can do that. That's pretty easy. I got a minus sign in front. Well, this integral breaks down. We're just integrating along the boundaries. And so up here, I've got positive heat transfer coming into the system. 1050 kilojoules, temperature is 525. And on this side, it's a negative because the heat transfer is negative leaving the system. So 700 at 350. And so, gosh, this is 2 minus 2. 2 minus 2 is 0. And so we get no entropy production. Well, that tells you right there that this is internally reversible because there's no entropy production. The other thing you can do is you can check the heat transfer. So if I take the 700 divided by 1050, that's 0.667 minus 1. So the actual efficiency of this cycle is 33%, 33.33. And then I can check the Carnot efficiency, which is 1 minus T TC over TH, and it's 0.333. So I get the same efficiency. So this one is internally reversible. So that's this one, it turned out to be pretty simple. So it's internally reversible. Okay. Next page. Close here. Okay. By supplying energy to a house at the rate of 25,000 kilojoules per hour, a heat pump maintains the temperature of the dwelling by 20 degrees at 20 degrees C when the outside air temperature is minus 10 degrees. Electricity is cents per kilowatt hour, determine the minimum theoretical operating cost to heat the house for 24 hours. Well, if this is a minimum, that tells you you get to use the Carnot heat efficiency, or COP efficiency, but we call it the coefficient of performance. And so let's go take a look at this quick. All right, so this is okay. So here's my diagram. This is my heat pump. So we have to put work into the heat pump. It picks up energy at the low temperature. That and the work together is rejected into the high temperature space that we want to keep warm when it's cold outside. Okay, we're given degree C. We got to work in degree K. So we add 273 to both of them. So TH is 293 and TC is 263. So then for the theoretical best coefficient of performance for a heat pump, we have gamma is TH over TH minus TC, so 9.7667. So that's my best efficiency. And I realized that this gamma is TH, so that's the TH divided by the costly input, which is the work, which is W dot. Okay, so this will let me calculate the amount of work, and I know that I also know that the work is TH minus TC. So going to this expression, 25,000 kilojoules an hour is what I'm putting into the house. So if I divide that by the COP, that gives me the work input. So I'm putting in 2559.73 kilojoules per hour here. And so that's what I have to pay for. And so remember, a kW is a kilojoule per second. This is kilojoule per hour. So I have to divide by 3,600 to convert to kW. And so I get 0.711 kW. And then, of course, 0.711 kW over 24 hours is 17.065 kilowatt hours. And then it's 8 cents per kilowatt hour. So that's $1.365, 36.5 cents. So that's my answer. So probably $1.37 here. Bingo. Steam is accelerated by an adiabatic nozzle from a low velocity, negligible, it just says low velocity, negligible, to a velocity of 220 meters per second at a rate, mass flow rate of 1.2 kilograms per second. If the steam at the nozzle exit is 300 degrees C at 2 MPa, what's the exit area on the nozzle? Okay. There we go, adiabatic nozzle. Okay. So we're just using this pretty simple expression here. The mass flow rate is volume flow rate, which is velocity times cross-sectional area divided by specific volume. Let's see. So we have to get the specific volume. And I think we had this as interpolation. We'll go look at the tables. So let's see. So we're at 2 MPa and 300. So 2 MPa. Yeah, so here's 2 MPa and we're 300. And so we're halfway in between. So that makes the interpolation. Add those two together, divide by 2. So it's 0.12 plus 0.1308 divided by 2 to get the specific volume. And so that's what we're doing here. So my specific volume at the exit is 4 meters cubed per kilogram. And then I know the mass flow rate, and so that's velocity times cross-sectional area divided by specific volume. I know the velocity, which is 20 meters per second, times A meters squared, divided by the specific volume. So solving this for A, I get 0.0000684 meters squared, and then that converts to centimeters. So I guess I got to divide by 1,000. Each meter has 100 centimeters in it. So divide by 1,000, 6.84 meters squared. Okay, that's the answer. So 6.8. Next page. 9, steam expands in a turbine from 6 MPa and 500 degrees C to 0.15 MPa and 120 degrees C at a rate of 1.2 kilograms a second. Heat is lost from the turbine at a rate of 34 kilojoules per second. During the process, determine the power output. We're going to throw away kinetic potential energy. So this is energy balance. Here we go. So DECVDT, the full-blown version for a single inlet, single exit. And of course, we're going to set that equal to 0. So this term will be 0. We have the heat transfer term. We have the work term. We have the mass flow, and we have enthalpy in. So it's pretty much plug and chug. So we know that the work is equal to the heat transfer plus m dot times h in out at 6 MPa, which is 6 bar and 500. So let's look at these. So 6 MPa and 500. Oh, 6 MPa and 500. So that enthalpy looks like it ought to be 3422.2. Check that. Okay, 3422.2, and then I'm 1.5 bar at 160. 1.5 bar at 160. Good direct lookup. That's easy. 2792.8. Okay, 2792.8. So just plugging everything in. The heat transfer is negative because energy lost from the control volume by heat, 1.2 kilograms a second. Enthalpy difference, so this calculates 7.1.28 kW. So that's pretty straightforward. 7.1. And then the last one, this one's, I don't know that we've done one of these, but at any rate, so what you got a well-insulated turbine, steady state, picture of it actually above. Steam enters at 3 MPa, that's at 1, and 400 degrees C, volume flow rate of 85 meters cubed per minute, so that's a volume flow rate. Steam is extracted from the turbine at a pressure of 0.5 MPa, as so not all the way through the turbine, so we have an extraction port on this turbine. So our extraction condition is 0.5 MPa at 180. The rest expands to a pressure of 6 kPa with a quality of 90%. Total power developed by the turbine is 11,400 kW. Kinetic potential energy, or effects are negligible. Determine the mass flow rate of steam extracted from the turbine at location 2 in terms of kilograms per second. Okay? So let's take a look at the solution. Here we go. So this is briefly restating. Looking up the properties. I'm going to let y'all do that. There's too many of them. If you go work through this and you have trouble with the properties, and talk through it. But 1 and 2 are just straight lookups. 3 is inside the saturation dome at that point, 6 kPa. And so you've got to go to the saturation table, quality of 0.9. So that's the enthalpy of the liquid at the low pressure. That's the HFG across the dome times 0.9 added on, and you get the exit enthalpy of 3225.84. Okay, so write a little equation here. So I'm going to let X equal to the steam extracted at location 2. So that makes 1 minus X, the steam that exits at the rear of the turbine. Okay. And so this will be the fraction. So then I can write this 11,400 is the total mass flow. So the total mass flow goes from 1 to 2. And then I pull X out, and then I have 1 minus X goes from 2 to 3 and exits the turbine. So this term should be the total work produced by this turbine. And of course, I need a mass flow rate. I'm given 85 meters cubed per minute. So at 1, when you look up this enthalpy of 1, you also note the specific volume, which is 0.0994 meters cubed per kilogram. And so 85 meters cubed per minute divided by 0.0994 meters cubed per kilogram is 855.13 kilograms per minute divided by 60, and you get 14.25 kilograms per second. Okay. And so then I have the mass flow rate, so I can plug in directly up here. So 11,400 is the mass flow rate, 14.2522 times these enthalpy differences. And so from 1 to 2, the difference is 418.9, and then times 1 minus X times the difference between H2 to H3, which is 486.6. So I'm just doing a little bit of algebra here. I'm solving for X, which is the fraction that is extracted of the total. And so the X came out to be 0.2164 times the 14.2522. It says I'm 3.084 is the extraction. So about 3.1 kilograms per second. 3.1. Okay, so I think that's the end. So let's submit a quiz. And yep, 50 out of 50. So those are the answers to this. So I'm going to stop this. I'll post this one, and then I'm going to do a little bit of lecture for the remaining amount of the class time for Tuesday, and I will send this out. Again, we're not going to meet in the classroom on Tuesday. You guys will have to, everybody watch the lectures that are posted on YouTube. Everybody's having a great day, and I'll be back in touch.